I welcome you to this third session of mensuration. In this session, we will take a look at some basic formulas and properties of areas and volumes. Basically, we will take a look at the formulas that concern 3D figures. To start with, let us look at cuboids, and you see there is a cuboid there with length, breadth and height. The volume of a cuboid is given by L into B into H, and the surface area is twice LB plus LH plus BH. Now remember, the surface area comprises of the area of 6 faces of a cuboid, and you will notice that L into B is the face that represents the floor and the ceiling. So LB for the floor and L into B for the ceiling, we have twice of LB. Similarly, twice of LH and twice of BH also are areas of some other faces of this particular cuboid. The length of the longest diagonal in a cuboid is equal to under root of L square plus B square plus H square, and there you see in the picture this is the longest diagonal of a particular cuboid. Now, what do we mean by painting four walls? Sometimes in questions you are asked not the surface area of the cuboid, but you are asked the area required for painting of four walls. So in this case, we only need to consider the surface area of four faces, which are the four vertical faces of a cuboid, ignoring the floor as well as the ceiling. So you see two opposite surfaces there. So each of these surface is L into H. So therefore, twice of L into H. Plus, you will have two opposite surfaces here where B into H is the area of each such face. So 2BH. So when we paint four walls, then the area in question is twice of LH plus twice of BH. Similarly, when a cuboid is cut into two by a plane, as you can see in the figure, this is a plane which cuts the cuboid. Then the cuboid is cut into two halves, not necessarily equal in this case, but one thing is certain, that the total surface area of the two smaller cubes increases by 2 into B into H. So the total surface area of the two cubes or the two smaller cuboids is more than the surface area of the original cuboid by a number which is equal to 2 into B into H, because B into H is the area of this surface, and two such surfaces they come out which were earlier hidden. Then we move on to cube. Volume of a cube is a cube, surface area is 6a square, and length of the longest diagonal of a cube is a under root of 3. Cylinders, volume is pi r square h, curved surface area is equal to 2 pi r h, and total surface area is equal to 2 pi r h plus 2 pi r square, the flat surface area on the top and the flat surface area on the bottom is added on to the curved surface area to get total surface area. So we have a cylinder, and you can see that by if we fold ABCD along its length, it will give rise to a cylinder like this. So here 2 pi r is nothing but the length of this particular sheet, and in case of a cylinder it is nothing but the perimeter of the base circle, and h is the height of a cylinder, and therefore 2 pi r h is the curved surface area, and you can see the curved surface area in orange. Cone, volume of a cone is given by 1 by 3 pi r square h. The curved surface area is pi into r into L. The total surface area is given by curved surface area plus the flat surface area, so which is equal to pi r L plus pi r square. L is the slant height as represented in the figure, r is the radius, and h is the vertical height of the cone. What happens if this cone is cut by a plane parallel to the base? If a cone is cut by a plane parallel to the base, and let us say that x is the height from the tip of this cone, and the overall height of the cone is h, then the volume of the cone, the smaller cone above, is given by x by h whole cube into the original volume of the cone. So x is the height from the tip and h is the overall height of the cone. So suppose we cut this cone at a height which is equal to 1/3 of the total height, then the volume of this smaller cone will be equal to 1 by 3 cube times the volume of the original cone. Another important point about a cone is how do you make a 3D cone from a 2D sheet? We can also make a cone from the sector of a circle. Many of you might have done this already. Maybe in your school carnivals or somewhere you must have already made a conical cap out of such sectors of circles. You see here we have a sector and there are points A and B. If I pull point A and B towards each other, then point O will rise perpendicular to the plane of your screens and it will give rise to a cone in this fashion. And you notice that the radius of the initial sector is equal to the slant height of this cone. So how do you generate an equivalence between the sector and the cone? So because the sector is of angle theta, theta by 360 into 2 pi r, that is the length of arc of this sector, must be equal to the perimeter of the base circle of the cone. So this is equal to 2 pi r, where small r is the radius of base of cone and capital R is the radius of the sector. On simplifying this, we will get theta by 360 into r is equal to small r. So that is one relation which we could remember. The other relation is theta by 360 into pi r square is the area of the sector. This must be equal to the curved surface area of the cone, and which will ultimately prove that the radius of the sector is equal to the slant height of the cone. This is another point that you need to remember in case of a cone. Sphere. Volume of a sphere is 4 by 3 pi r cube. Total surface area of a sphere is 4 pi r square. So with this we come to an end of this particular session on mensuration. In case you have any feedback, any doubts or any query, please feel free to write to us at studentservices@pfindia.com. Thank you very much.